Hi everyone, and welcome to today's session. Today we are looking at performing sensitivity analysis for financial decision making. We can say that sensitivity analysis is just a technique that we have to understand to comprehend how variations can match variables. For example, the output variable such as profit. Like if I told you income or costs, how is it going to affect your profit? If at all you make more revenue, you generate much revenue, how is it going to affect your profit, your output? Of course, if at all you generate more revenue, that will be high profit. If at all you incur much costs, that will be a loss. Yes, so we want to look at the various several sensitivity analysis tools that can aid in financial decision making. So far, we have the what if analysis that talk about the data tables. We find the goal seek, we find scenario manager, and then we have a standalone sensitivity analysis tool, which is known as solver. So we shall start by looking at each one of them, but when it reaches to practicals, I will be starting with solver. So with goal seek, we can say that you use that tool to find the input value needed to achieve a specific output. First of all, it is a reverse calculation. What we mean, in order to use this tool, you need to be knowing, you need to be in the know of your goal that you want to achieve, and therefore you basing on that goal, you use the goal to find the input value that you need to achieve that specific goal. Okay, so when we look at the scenario manager, for it manages multiple sets of scenarios. We can say multiple sets of inputs. So it helps you to look at what will be the best scenario, what will be the worst. And in most cases, those scenarios focus on they are to do with financial scenarios. So scenario manager helps you to know the best scenario that you can choose from amongst all the alternatives so that you can make the best financial decision ever. Okay, so when we look at data tables for them, they are basically looking at how changes in one or two variables affect the results of the formula. So for it looks at several variables affecting the result, affecting the end result. Okay, then when we look at solver is basically an optimization linear programming tool, and for it is used to determine the value of a target cell. And basically it works by changing the multiple inputs. So you can use solver in resource allocation, cost minimization, and profit maximization. In most cases, solver works like goal seek. Solver works like scenario manager. So with solver works with goal seek. It works like goal seek, just that for goal seek it is dealing with only one variable, but for solver you're dealing with very many variables. Then for data tables work the same way like scenario manager. So we can start by looking at the today we are going to look at several calculations, and we shall begin with solver. So when we come to solver here, first of all, to make use of solver, you must be knowing how to formulate a particular model. So with solver, you're either maximizing the profit or you're minimizing the profit. And remember, whatever you do with solver, you start with a model formulation. We start by building a prototype. Which prototype you're going to base on to reach a particular output. So with solver, you start by identifying the problem at hand, and in most cases that problem is solvable by linear programming. Everything has to be linearly aligned to each other so that we can find the optimal solution. You're going to see how that works. What we mean by linearly aligned linearly to each other, let's look at this. When you look at this example here, the red cars are linearly aligned to their car components. The blue cars are linearly aligned to their components. The green car models are linearly aligned to their car components. When you look at yellow, it is the same thing. Orange, it is the same thing. Okay, so this is what we mean by linear programming. We use linear programming while using Excel solver to find optimal solutions to our specific problems. So when we go back to, remember we said we start by identifying the problem at hand. Then from there we formulate a mathematical model of the unstructured problem. Why are we saying unstructured? Because you've not yet known the steps to follow to solve the given problem. You just have a problem at hand, like you've not yet formulated a solution because you don't know what to do. So what you do, you just formulate a mathematical model for that unstructured problem so that you can go ahead and solve that problem by using solver. Solver can make it to become structured upon finding the solution. So after solving the problem, we can go ahead and implement it. We can go ahead and implement that solution that solver has given us. Okay, so you implement the solution, and therefore we can, based on that, to conclude that solver has been able to find for us an optimal solution. Okay, then the assumptions for this kind of model, the solver model, it assumes linearity, as in the impact of decision variables is linear in constraints and objective functions. This is what we are talking about. These decision variables you see here, here and there, they are linearly aligned to the objective function. So that's what we are saying, that it assumes linearity. Okay, then from there we can say that divisibility and integer values are acceptable. So in some cases solver accepts non-integer variables. Then certainty values of the parameters are known and constant. You find that whatever you input under the Excel solver, you already know it. Then non-negativity, you find that negative values of a decision variables are not accepted. It is either greater than or equals to 0. Solver doesn't accept non-negativity. It doesn't accept negative values. So it is a non-negativity programming tool. Okay, so in solver, we expect 4 components as we are using solver. First of all, you must be having the decision variables. Decision variables, in most cases, they represent the levels of activity of a firm. Like to what level does a firm, is it active? Yeah, or it can be available in terms of amounts. Yeah, in terms of quantities there, you get to know that this is a decision variable in our model. For example, in this example here, the production levels determine the quantities of the firm's production. Therefore, we shall regard this as our decision variables. Then the objective function as another component. First of all, it is a linear mathematical relationship describing an objective of the firm. Yeah. So in most cases, this is based on the decision variables because they are the decision variables that will determine your outcome levels. Yeah. So when you come here, these production levels are going to determine your amount of profit that you are going to make at the end of it all. Okay. So that's why we are saying that this objective function is normally based on the decision variables. So this function, you either maximize profits or you minimize costs. Okay. Another component, we have the constraints. Constraints are basically limitations. You can call them restrictions that are placed on the firm by the operating environment. So they are basically those limitations that restrict the availability of resources. Yeah. As in how feasible is the solution as compared to our available resources. These are constraints. They set a limitation to restrict the available alternatives. Because if I tell you have available alternative solutions and many of them do not fit within your limitations of resources, of available resources, then you have to select one that fits within your budget. Yeah. So we normally set constraints by using algebraic functions. As in the algebra functions, you find the greater than or equal to, the less than or equal to, the equal, the integer, yeah, as we shall see in our practical bit of it. Then we also have parameters. Parameters are numerical coefficients. Those numerals that you normally have to deal with while using the Excel solver. They are basically known as the parameters. So these are basically the components that we normally use as we are dealing with solver. So upon opening our solver, we shall expect to see all these. Okay. So we got a problem here, the product mix problem. Here we are asking ourselves as Toyota Uganda, how many car models should be produced to maximize profits given the materials? Much as we have an unstructured problem here, we are still assuming a production level of 1010 per each car model while making these profits per unit of each car model. We want solver to determine the exact levels of production that we need, the amount of each car model that we need to be producing to maximize profit while fitting within our available resources, and those are the parts on hand. Okay, so before we can go ahead to compute that, we see here the resource availability. It means that our limitation is set to be at only 200 parts. Yeah, so the decision variables are the car models, the levels of production, yeah, of the various car models from X1 to X5. The objective function, we are maximizing profits, and for us to maximize profit, we shall need to get we shall need to get the product of each profit per car, as in the product of each profit. The product of profit per unit of a given car model, yeah, times the levels of production. As I told you, these levels of production are represented by, for example, if I put here my cursor, this is X1, this is X1, this is X2, yeah, this is X3, this is X3, this is X4, this is X5. So the reason as to why we are saying that to get the total profit per unit, we are saying 95 X1 plus maybe 30 X5. What we mean there, I guess we can see that here. As in here, the objective function, we should get a 95 of the red car model. As we can see here, 95 profit per unit of the red car model times X1. X1 is represented by a 10. Yeah, that's why we are saying 95 X1, meaning we have to multiply the profit per unit with its associated units produced. Okay, that are represented by X's. Then plus, yeah, plus maybe the profit per unit of blue cars times X2, which is 10. The profit per unit of green cars times X3, which is 10. In this case, we just borrowed a sample of red and a sample of yellow to mean that we have to cover up each and everything from red to orange. Okay, so that's why here we just got a sample and we're like 95 X1. This $95 represents the profit per unit of red cars and its associated units of production represented by X1 plus the $30 of profit per unit of orange cars times its levels of production as in the units produced, which is represented by X5. Okay, so that's how we shall determine the objective function. Then for us to be able to, these are the resource constraints as in the limitation set, so that we can be able to select the most viable alternative solution to our problem. As we said, Solver is a non-negativity linear programming tool. There shouldn't be negative variables at all in Solver. That's why we are saying from x1 to x5, this should be either greater than or equal to 0. From x1 to x5, this should be integers. Then when we look at the resource constraint number 1, as in x1 times, for example, let me show to you here. Yeah, so this means that x1 times the levels of production plus x5 times its no. This is this times the car components, okay? Yeah. So what we mean here is parts required should be less than or equals to parts on hand, as we can see here. That's what they mean here, that x1 plus x1 times its levels of production times its car components plus x5 times its car components should be less than or equal to 200. Yeah, so we shall get back there when we start our calculations. So when we move to the solution types, in Solver we either get a feasible solution or an infeasible solution. A feasible solution is one that does not violate any of the constraints. An infeasible solution violates at least one of the constraints. You find a constraint like this, x1 to x5 should be greater than or equal to 0, but you find a solution in that some values are negative, so in so doing the constraint is violated. Then you find this one is telling us that it should be less than or equal to 200, but you find some are exceeding 200, then that is an infeasible solution. A feasible solution is one that that satisfies all the constraints. Yeah, it is binding. Are we together? So when we move to here, we in most cases, after getting the solution, Excel Solver normally shows to us a slack variable and a surplus variable. In most cases, a slack variable represents those resources that have been unused. So in most cases, just as here we have 200 parts on hand, but you find here the parts required, you have maybe 50. It means the 150 has not been used. So in that case, the 150 will be the surplus variable. Or you find we have 200 parts here, but here parts required are 250. It means the 50 will be the surplus, the excess of what is available. Yeah, you find that each of these variables contribute nothing to the objective function, because just imagine if you've said 200 parts, yeah, but you've only used 50 to maximize your objective, then the 150 has contributed nothing towards the maximization of your objective. Also, the surplus variable contributes nothing to the objective function, because if you have 200 parts at hand but you require 250, then the 50 contributes nothing to the objective function, because you do not have it at the moment. Okay, when we get here, so in most cases, these are the typical areas of problems that we are dealing with in Solver. We are either determining the optimal schedule. Each individual task must align with your ultimate goal. Like whatever you do should be aligned to your ultimate goal. Establishing locations of a particular business, identifying optimal work job assignments, determining optimal dietary plans, identifying optimal mix of products in a factory, and etc. So having understood and formulated a foundation about Solver, let's see how it works.